Alright, in this video we're going to explore some important trig identities and try to convince ourselves that they make sense, try to understand them. Alright, so I thought we'd go down this list row by row. Each row is arguably a set of related identities. So we could start by looking at these identities. Like to think of these as being the period identities because 2 pi is the period of the sine and cosine functions. When we explore these identities, we can often look at them in general. We can often look at them both in terms of a unit circle and in terms of a wave, the graph of the functions on the coordinate plane. So we'll try to do that in both ways, try to understand these identities in both ways here. The first one here we could start with, that cosine of theta equals cosine of theta plus 2 pi. These really come together. The other identity is that the sine of theta equals the sine of theta plus 2 pi. And really this can be simplified down to the idea that theta and theta plus 2 pi are coterminal. So let's just go ahead and draw a quick sketch of a situation that could be represented by this scenario. So suppose here, let's just kind of arbitrarily draw an angle called theta, and we can go and find its the point on the circumference of the circle specified by that angle theta. And we know that the coordinates of this point are cosine of theta, sine of theta. And now let's go ahead and contemplate what happens if we look at an angle called theta plus 2 pi. So theta would rotate us to that same orange line, and then the plus 2 pi part rotates us around an entire additional revolution. So this green angle could be thought of as theta plus 2 pi, and it terminates at the exact same spot. So it has the same point on the circumference that it specifies, and therefore the coordinates of that point are cosine theta plus 2 pi, comma, sine theta plus 2 pi. And we can see that this means that cosine of theta plus 2 pi and cosine of theta must be equal, and the sine of theta plus 2 pi and the sine of theta must be equal. And so in that way we can justify these identities. The other way to look at it is in the perspective of the wave graphs. As I mentioned before, I think of these identities as referring to the period of the sine and cosine functions. And so if we highlight a period of the cosine wave, this first 2 pi units worth of the cosine graph, what we can do is shift that portion of the graph left 2 pi units, and it'll land right back on the graph again, showing that if we shift the graph horizontally 2 pi units, we get the same graph again, showing that if we shift the graph to the left 2 pi units, we get the original graph again. And similarly with sine, it's basically saying the exact same thing. So we could highlight a period worth of the sine graph. We could use this. Let me start over on that one. Use this portion of the sine graph, and then I can grab onto it and shift it to the left exactly 2 pi units, and it lands right back on the graph, suggesting that a shift to the left 2 pi units doesn't change the graph, gives us the same graph. And so in that way, we can verify that these identities are true. All right, let's go to the next set on the table. All right, the next set of identities on our table are these identities. I like to think of these as the shifting identities. So let's go ahead and explore those on the next page. Got those focused on. And so what we know from our study in Math 111 or a college algebra course is that this adjustment on the inside of the cosine graph causes the cosine graph to be shifted to the right pi over 2 units. And so what we could do is take this cosine graph that we've got here and go ahead and shift it to the right pi over 2 units and see if the result looks like the sine graph. So I'll go ahead and highlight the cosine graph here. And then I'll shift it to the right pi over 2 units. Let's quickly observe what that's going to mean for us. Our cosine graph has, for example, a peak here along the y-axis. We're going to want to shift that point along with all of the points to the right pi over 2 units, and so we'd want that point to end up there. And if we take this entire cosine graph and shift it to the right pi over 2 units until the peak falls on that pink dot, and then step back and look at our graph, it does look exactly like the sine graph. Notice that the sine graph is increasing, passing through the y-axis here. It's at its midline going up through the y-axis, and that's exactly what behavior we've created. That's a way that I'll encourage us to consider the difference between sine and cosine, is to focus on what's the behavior at the origin along the y-axis, and we see that sine is increasing along the y-axis, and so when we see that behavior, we recognize it as being the sine graph. All right, and so now let's look at the other situation. Here we have a similar adjustment on the inside of the sine function that will cause a horizontal shift, but here we'll shift in the other direction. We'll have a shift to the left pi over 2 units. And so let's quickly review what that would look like. Sine is at a peak here at pi over 2, and if we shift that to the left pi over 2 units, we'd expect that peak to land on the y-axis there. So let's go ahead and actually shift this graph around. So I'll again highlight the sine graph and then grab onto it, and we'll shift it to the right pi over 2 units. Sorry, this isn't the most technical kind of mechanism that I'm using here, but we can kind of get a sense of what it looks like. And the way that I encourage us to be familiar with the cosine graph is to notice that cosine is at a peak at the y-axis, and then notice this graph after we've shifted is at a peak at the y-axis, which shows that this shifting of sine to the left actually gives us cosine. And so we see that these two identities are in fact true. All right, let's go to the next set of identities. All right, now we can move down our list and look at the next set of identities. I like to think of these two identities as referring to the symmetry of the graphs of the sine and cosine functions. We'll consider that when we get down to the wave versions of these discussions. But first we'll look at the unit circle. And our first identity here is that the cosine of negative theta equals the cosine of theta. To make sense of this identity, we're going to want to draw a picture that involves both the graph of a angle negative theta and an graph of an angle positive theta. So we can arbitrarily choose what angles we choose to draw. I'll just draw pick that for theta. And if that equals theta, then theta terminates at this point. And to find its cosine value, we'd walk down to the x-axis and determine how long that horizontal coordinate is. And then we can play the same game with negative theta. Negative theta is just as big as theta, but it's rotating in the opposite direction. So that'll take us out to this point, which terminates here. And then we can walk ourselves down to the x-axis to find out where the x-coordinate is. And look at that, they're the exact same length. And so we see that the cosine of the opposite of theta and the cosine of theta are the same. Now regarding the version of this discussion concerning the wave, this identity that the cosine of negative theta equals the cosine of theta, this means that the graph of the cosine function is even. Even is a term that describes a type of symmetry, specifically a type of symmetry about the y-axis. So this y-axis is the center of the symmetry for this function, and what we mean by that is that the portion of the graph on the right side of the y-axis is a mirror image of the portion of the graph on the left side of the y-axis. So this identity informs us that the graph of the cosine function is even. And then we can look at the sine identity. The sine identity also involves an angle opposite of theta and the angle theta. So let's go ahead and construct situations where we have those two angles. So we'll arbitrarily just go ahead and put theta in quadrant 2, like we've been doing, terminate it here. There's its terminal side, and we know that the vertical coordinate of the terminal of the point that of intersection on the circle, the vertical coordinate is the sine of the angle. And now we can plot a angle negative theta. Negative theta rotates us down here into quad 3, and we terminate there. And then the sine of negative theta would be this distance here. And we see that these two lengths are the same. It's just the pink one is negative. And so the sine of an angle is always the opposite of the sine of the opposite of the angle. That the sine of an angle and the sine of the opposite of the angle are the same in magnitude, but they would have the opposite signs. And when it comes to the wave graph, this fact about the sine function informs us that the sine function y equals sine of theta is an odd function. And an odd function means that a graph is symmetric about the origin. The origin here, the point 0, 0. And it has to do with rotating the graph. If we could rotate this graph 180 degrees around the origin, it would land back on top of itself. But from our perspective, since I can't spin the graph around, what we notice is that the shape on the right side of the y-axis is sort of the same but opposite of the shape on the left side of the y-axis. So rather than being mirror images like the cosine graph, they're sort of opposite mirror images here in the sine graph. All right, let's go back to our table of identities. All right, now to the last pair of identities on our list. Okay, so let's first look at this cosine identity, that the cosine of theta equals the cosine of 2 pi minus theta. So we have to draw on our unit circle situation where we have an angle theta and we also have an angle 2 pi minus theta. Notice that this angle 2 pi minus theta can be understood as 2 pi plus negative theta. I think that might help a little bit in orienting ourselves about this angle theta. So if we call theta some first quadrant angle, say there's theta and it terminates here. And then that of course would mean that this distance, this red distance here, is cosine of theta. And now if we try to construct this angle, 2 pi plus negative theta, what we could do is first rotate 2 pi, so a full revolution is 2 pi, and then we'll add to that the opposite of theta, and that'll take us to this terminal side. And if I'm able to draw this more accurately, we'd see that they share the same cosine 2 pi minus theta. They share the same cosine value. What I probably should have emphasized here was that it's a bit hard to do it. This angle that starts on the positive x-axis and rotates all the way around and hits that green line, that's 2 pi minus theta. And so we see that because of the sort of symmetry of a circle and the nature of the cosine function, that the cosine of theta and the cosine of 2 pi minus theta will be the same. And now if we look at the sine identity, the sine of an angle theta equals the sine of pi minus that angle theta. We want a situation where we can look at an angle theta and an angle pi minus theta. Similarly, I think it might be worth considering that the expression pi minus theta is pi plus the opposite of theta. And we can give ourselves a situation with our angle theta in quadrant 1, terminates here, and there's our our sine value. This is the sine of the angle theta. Now we want to plot the angle pi plus negative theta. We want to plot this angle pi plus negative theta. So what we can do is we can rotate pi, which is half of a revolution. There's our pi rotation, and then we'll add to that the opposite, a backwards rotating version of theta, to take us up to this terminal side. And if we do it properly, the vertical coordinate here, due to the symmetry of the circle and the definition of the sine function, the sine of pi minus theta is exactly the same value as the sine of theta. All right, and that takes us through these identities.